Somewhere in the solar system, there's a dead twin of Earth, roughly the same size. Once, it had a thick atmosphere, rivers, lakes that sat still long enough for sediment to settle into layers, just like lake beds on Earth. For a time, you couldn't have said with confidence which world was more likely to support life. Then everything changed. Earth kept its engine running. Mars is shut off, not violently, as far as we can tell. It just stopped. That's what makes Mars so unusual. On Earth, geology is constantly rewriting the landscape. Mountains rise, continents shift, rivers erode, and old surfaces disappear. Mars barely does any of that. The evidence was never folded deep underground or erased by billions of years of recycling. It's still there, exposed in the dust and the rock. Mars isn't just a dead world, it's a fossil. The only preserved record we have of what the early solar system looked like. For most of the last decade, the story of Mars has been fairly straightforward. A small planet, weak gravity, a cooling core. The magnetic field disappears. The atmosphere is stripped away. End of story. It's a good explanation, but not the whole one. Over the past few years, new seismic measurements have shown that Mars isn't quite as geologically simple as we thought. The planet is still dead by almost any definition, but not in the way we imagined. And that changes when, and possibly how, Mars became the world we see today. To see why, we have to go back to the beginning, when Mars and Earth were far more alike than they are now. Mars has about 10.7% of Earth's mass, close enough to call it a tenth. That doesn't sound like much until you think about what it means for a planet. Smaller worlds lose heat more quickly. They have less heat to begin with, and more surface area relative to their volume through which to lose it. That single difference shaped almost everything that followed. But at first, Mars and Earth looked surprisingly alike. During the Noachian, between about 4.1 and 3.7 billion years ago, rivers carved valleys across the Martian surface. Lakes persisted long enough for layers of sediment to build up on their floors. The atmosphere was thick enough to keep liquid water stable, at least for long periods of time. Earth wasn't all that different. It was volcanic, geologically restless, and wet across much of its surface, still settling into the planet we know today. Two rocky worlds, forming only a few tens of millions of kilometers apart, following remarkably similar paths. They didn't stay that way. Mars's smaller size meant its interior cooled more quickly, and inside a rocky planet, heat isn't just warmth. It's the energy that keeps the outer core moving, a vast ocean of liquid metal, constantly churning. That motion acts like a dynamo, generating the magnetic field that shields a planet from space. In 2018, NASA placed a seismometer on the Martian surface as part of the InSight mission. Its purpose was to do something we'd never done before: listen to the inside of another rocky planet. Every marsquake sent vibrations through the interior. As those waves traveled, they sped up, slowed down, bent, and reflected depending on the material they passed through. From that, scientists could begin to map what lies beneath the surface. What InSight revealed was surprising. Instead of finding a completely cooled interior, InSight revealed a liquid metallic core about 1,675 kilometers in radius. Above it sits another surprise, a layer of fully molten silicate rock, roughly 150 kilometers thick, that earlier models hadn't predicted. That means if you could stand on Mars and somehow drill straight down, you'd pass through around 150 kilometers of molten rock before ever reaching the metal core, which is still liquid itself. So was Mars's interior ever completely frozen? Apparently not. By almost every measure, the core is still largely molten. The surprise isn't that Mars froze solid, it's that it didn't. And yet the magnetic field vanished anyway. A planet with a mostly liquid core should, in principle, still be capable of generating a magnetic field. Somewhere between a molten interior and a dead magnetosphere, something else changed. Mars doesn't have a global magnetic field today. The Mars Global Surveyor confirmed that in the late 1990s. But it also found something unexpected: patches of intensely magnetized crust concentrated almost entirely in the ancient southern highlands. Those rocks preserve a record of a very different Mars. They could only have become magnetized while a global magnetic field was active, aligning tiny magnetic minerals as the rock cooled. So at some point in its early history, Mars clearly had a planet-wide magnetic field. The question is when it disappeared. For years, the leading explanation seemed straightforward. Several of Mars's largest impact basins, more than 800 kilometers across, and formed between roughly 4.1 and 3.7 billion years ago, show almost no magnetization. If a global magnetic field had still existed when those impacts happened, the newly formed rocks should have recorded it. They didn't. The simplest conclusion was that the dynamo had already shut down. But that may not be the only explanation. A 2024 study modeled what would happen if Mars's ancient magnetic field reversed polarity, the way Earth's does today. If those reversals happened often enough, more than 90% of large impact basins would appear effectively demagnetized when viewed from orbit, even if the dynamo below was still active. That means the evidence can be read in two different ways. Mars may already have lost its magnetic field by about 4.1 billion years ago, or the dynamo may still have been running, with a reversing field that left a much weaker signal than scientists expected. At the moment, the evidence doesn't clearly favor one picture over the other. But whatever the exact timing, the consequences are still written across the surface of Mars. Jezero crater lies on the edge of Isidis Planitia, a vast impact basin near the Martian equator. The crater itself is about 45 kilometers across. More than 3.5 billion years ago, a river flowed into it, slowing as it entered the basin and leaving behind a broad fan of sediment. A delta, much like the ones rivers still build on Earth today. Since landing in February 2021, Perseverance rover has mapped that delta in remarkable detail. The cliffs are made of flat, horizontal layers, laid down one after another as the lake filled, receded, and filled again over long stretches of time. Stand at the base of those cliffs, and each band of rock becomes a page in that history. Layer after layer of sediment settled onto an ancient lake bed long before complex life appeared on Earth. Which is exactly why geologists care so much about this place. Earth has spent billions of years recycling its surface. Plate tectonics buries old rocks, mountains erode, and continents are constantly reshaped. Mars does almost none of that. The delta remained where it formed, preserving a record that Earth would almost certainly have erased. By late 2023, Perseverance had collected 23 samples from Jezero, including one known as Otis Peak, which is unusually rich in phosphate, a key ingredient in the chemistry of life as we know it. Then, in 2025, another sample from a rock called Chayava Falls revealed what the journal Nature described, after a year of peer review, as a potential biosignature. Evidence consistent with past microbial activity, but not proof that life once existed there. The rocks have preserved their story. We're still trying to understand what it's saying. The closer we look at Mars, the more complicated its story becomes. It wasn't simply a planet that cooled down and switched off. We now know Mars's interior never completely froze. Even today, scientists don't agree on exactly when Mars lost its magnetic field. One thing is clear. More than 3.5 billion years after water stopped flowing through Jezero crater, its river delta is still there. Layer after layer of sediment remains almost exactly where it was left, waiting for a rover to read a history that Earth has long since erased. Our planet is constantly rebuilding itself. Mars largely stopped, which is why its oldest history is still there for us to read. That's the real legacy of Mars. Not simply that it died, but that so much of its past survived. And one last thing. That cross-section you saw at the beginning wasn't an artist's guess or an outdated textbook diagram. It's based on what the InSight mission revealed about the planet's interior. The surface stopped changing. The inside never fully did. The universe has more stories to tell. See you in the next one.